For decades, scientists have been trying to understand a mysterious substance called dark matter. We can't see it, we can't touch it, but we know it's there because of how it shapes the motion of stars and galaxies. In fact, over 80% of the universe's mass seems to be made of this invisible material. But what exactly is it? At first, astronomers thought dark matter might just be normal stuff, objects that are hard to see, like brown dwarfs, dead stars, or black holes. But the more we searched, the more these possibilities were ruled out. There simply aren't enough of these objects to explain what we observe in the universe. So researchers turned to more exotic explanations, hypothetical particles that interact through gravity, but not through light or regular matter. These include neutrinos, axions, and other theoretical particles. Scientists have built extremely sensitive detectors to catch these elusive particles. But after years of effort, we still haven't found a clear signal. That brings us to another possibility, something that's been considered before but is now being looked at with renewed interest: primordial black holes. These aren't the black holes formed by dying stars. Instead, they would have formed just moments after the Big Bang, during the earliest stages of the universe. Back then, the universe was a hot, dense soup of energy and matter. If certain regions were just slightly denser than others, they could have collapsed under their own gravity and formed black holes, no stars required. Depending on the conditions, these primordial black holes, PBHs, could have formed with a wide range of masses, from less than a gram to thousands of times the mass of our Sun. But the most interesting mass range, at least when it comes to explaining dark matter, is the asteroid-mass range, between 10 to the power of 17 and 10 to the power of 23 grams. That's roughly the mass of a small asteroid, far smaller than a star, but still massive enough to bend space and time. If dark matter is made of such small PBHs, they would be spread across the galaxy, moving at high speeds through interstellar space, and occasionally one might pass through our solar system. You might think we'd never notice such a tiny, invisible object zipping through space. After all, PBHs don't emit light, and in the asteroid mass range, their event horizons are smaller than atoms. But while we can't see them directly, we can detect their influence through gravity. When a PBH passes near a planet, its gravity can cause the planet to change its motion ever so slightly. The change might be tiny, just a fraction of a millimeter per second in speed, but over time, it adds up. After years or decades, this small nudge could cause a planet to drift slightly from its expected position, maybe by a meter or so. Mars, it turns out, is an ideal place to look for such tiny shifts. For more than 20 years, we've had multiple spacecraft orbiting Mars, sending back highly accurate measurements of its position relative to Earth. Using signals traveling at the speed of light, scientists can calculate the distance to these spacecraft with astonishing precision. We can now track Mars's orbit with an accuracy of about 1 meter, possibly even better. So what happens if a PBH passes near Mars? It would slightly tweak the planet's orbit. That small change might not be noticeable at first, but after a decade, it could result in Mars being a full meter away from where it was expected to be. And thanks to our precise tracking, we might be able to detect that. This leads to two potential experiments. First, we can analyze past data. With 20 years of high-precision observations, researchers can look for any unexplained shifts in Mars's orbit. If they find multiple instances where Mars's position doesn't match predictions, and if these can't be explained by known asteroids or gravitational interactions, then PBHs become a serious suspect. Second, we can continue monitoring future data. If we're lucky, a PBH may pass close enough to Mars in the coming years to create a detectable change. And if we detect such a shift in real time, we might even be able to search the sky for the object responsible. If it's a regular asteroid, powerful telescopes should be able to spot it. But if nothing is seen, if there's no visible object causing the change, then a primordial black hole becomes a strong possibility. Of course, this isn't proof. A single unexplained gravitational effect could be due to something we overlooked. But if we see too many such anomalies to explain with normal matter, then PBHs become not just possible, but likely. What makes this idea so exciting is that it turns the entire solar system into a giant dark matter detector. We don't need to build a collider the size of the galaxy. We already have Mars, Earth, and other planets moving like clockwork under the laws of gravity. Any disruption to their paths could be a message from a tiny black hole flying by.